There are about 3,000 approved drugs treating just over 3,000 diseases. The other 9,000 human diseases have no approved treatment. An example of such a disease is long COVID, which affects huge numbers of people to this day. Many diseases share similar mechanisms of action, hence can be treated with repurposed drugs. That is, already approved drugs can be applied to treat new diseases. However, too often, there is too little incentive for companies to pursue this. Hi, I'm Alexei, and I did my fellowship project with a non-profit organization called EveryCure, which aims to save lives through drug repurposing. But how do we find repurposed drugs? Clinical trials are extremely costly. Our strategy, therefore, is to train a machine learning model which gives a probability score, predicting the chance that a given drug treats a given disease. Only the drugs and diseases with the highest probability score go on to be tested in clinical trials, possibly becoming new cures. So the better the machine learning model is, the higher the chance of a successful clinical trial, and the higher the chance of finding a new cure. The current state-of-the-art model used by EveryCure is called KGML XDTD, recently published in the journal Gigascience. This model uses knowledge extracted from thousands of biomedical articles encoded in a data structure known as a biological knowledge graph. The aim of my fellowship project was to build on top of this model in order to enhance its predictions. At the beginning of the project, I tried several approaches to determine which could create the most impact in a given time frame. Notably, I implemented neural network models and embedded chemical structure information into the model. However, one approach stood out, and that was XGBoost, a popular boosted decision tree model, combined with Bayesian hyperparameter optimization, a technique which can be thought of as learning the best way for a model to learn. So that's the end of the story, right? Not quite. About midway through my fellowship project, my XGBoost model was highly accurate on the test data set. So I applied it to a real disease, long COVID. To my dismay, it produced nonsense, essentially. It said something like 2/3 of all drugs treat long COVID with more than 90% probability, which is clearly false. I had to think fast in order to fix this and understand what the underlying cause was. As it turns out, the problem was that the previous dataset used for training and for testing only consisted of drugs known to treat diseases, drugs known not to treat diseases, but it did not take into account the fact that a random drug and a random disease have no known relationship. Once I understood this, the fix was clear. I could generate synthesized data consisting of random drugs and diseases. The new model gave much more sensible and interesting results. Furthermore, this made me realize that we can generate as much synthesized data as we like, which, as it turns out, gives a significant performance boost. My final model achieved significantly improved test scores compared to the baseline model. In particular, the mean reciprocal rank score, or MRR, is an important metric measuring the chance that the model ranks a drug disease player constitution a cure higher than one that doesn't. This metric was improved from 0.39 to 0.65. To translate this into plain English, a conservative estimate shows that the new model is roughly 1.3 times more likely to find a cure compared to the baseline model. Finally, once the models were trained and evaluated, I generated a list of predicted drug treatments for long COVID, and I've passed this onto a team with medical expertise. With the hard work of the wider EveryCure team, this could lead to new treatments for long COVID.